Hi, welcome to this lecture on AVL Trees. My name is Dr. Ritesh Ajida. We found in the last lecture that when we considered binary search trees, we found with a height h, the space used was on, and you could get the floor entry, get any value, get the ceiling entry, put an item into the key, the binary search tree, and erase items in OH time, where h is the height of the tree. We also spoke about the benefits of using balanced binary search trees. However, we had no way to maintain a balanced tree with the standard definition of a binary search tree. So that's the motivation for this lecture. We found in the last lecture binary search trees, depending on the height of the tree, dictated the complexity of the methods for the tree. However, if we had some mechanism to keep the tree balanced, we found significant computational savings in using the binary search tree, because a balanced binary search tree will allow us to retrieve items in log n, log base 2n. It'll allow us to insert items in log n because the height is balanced. It'll also allow us to erase items in log n. So we actually would really like to keep the tree balanced, because if we can find things very quickly. We'll find things very optimally, which will dictate significant computational savings. So that's what we would like, introducing AVL trees. Now, AVL trees do just that. They attempt to keep the tree balanced. If we can keep the tree balanced, we will enjoy the computational savings which it provides from a balanced tree. We'll be able to find items in log n time. We'll be able to add items in log n time. We'll be able to remove items in log n time. Now, if the tree was balanced, and we couldn't guarantee that before. So AVL trees, as I said before, are balanced trees, and we call them height balanced trees, and I'll explain that in a minute. An AVL tree is a binary search tree, which means that it has that property from the last slide. I'll go back to that property so it's crystal clear. A binary search tree, here is the property. Let U, V, and W be three nodes. This can be any three nodes, right? As long as V is the parent, U is the left child, and W is the right child. It can be any. It can be these three nodes. It can be these three nodes. It could be these three nodes, and so on. We have this site restriction. We could remove the equals to here if the keys are unique, and you can say key U is less than key V, which is less than key W. So that will be a binary search tree. So we know that AVL trees, according to this definition, are binary search trees, which means they inherently have that definition. Such that for every internal node V of t, okay, that can be any internal node. That means any of these black nodes, not the blue nodes. The heights of the children of V must differ by at most 1. So let me give you an example of that. So let's crystallize this. Heights of the children of V can differ by at most 1. So looking at this node, number 32, it has a height of 1. Okay, so that's the height. See, there's one layer beneath it, so it has the height of 1. These have the height of 0. 48 has the height of 1. 62 has the height of 1. 88 has the height of 1. 50 has the height of 2, because there's 2 layers beneath it. Okay, 78 has the height of 3, because there's 3 layers beneath it. 1, 2, and 3. Okay, another way of thinking about this is just adding 1 to the highest height between the two children. So 78 has the children 50 and 88. We pick the highest heights of those two children, which is 2 in this case, and we just add 1, which gives us the height of the new node. This is another way you can compute it very quickly when you're programming solutions. So here is 17, which has the height, well, the height of the left child is 0, the height of the right child is 1. So let's just take the highest, which is 1, and add 1 to it, which gives us 2. Okay, we take the highest height between 17 and 78. You can see this is a recursive definition, which is 78 has the height of 3. I'll just highlight it for you. So all we do is between 3 and 2, which is larger. 3 is larger. We add 1 to that, which gives us the height of 4. Okay, So that's how we get the heights of every node. So we're trying to find out if this tree is height balanced. Okay, we call it height balanced. And height balanced means height of the children of V can differ by at most 1. Differ by at most 1. So that means that if you subtract the heights of the two children, then we should get a value either -1, 0, or 1. If we get anything else, any other integer, that means that this that subsection of the tree is not height balanced, and something needs to be done to fix it. But we won't talk about that something right now. I just want to get the definition across. So let's see if this tree is height balanced by subtracting the heights of each of the consecutive children. So I'm going to now look for my pen. I have to find it. I'm sorry. Let's see. This is here's a pencil. I'll make it blue and I'll close it. Right. So we're going to do some subtraction now. We say 48, okay, is the one node, and 62 is the other. Okay, and this is the height of 1. This is the height of 1. Right? 1 minus 1. Okay, 0. So the height factor of this node is 0. The height factor, I'm writing it in a different color, right? The heights are given in black. The height factor is given in blue. Okay, so we got the height factor of 50. The height factor of 62, 0 minus 0. Okay, it will be 0. The height factor of 48, the node 48, is going to be 0. The height factor of 88 is going to be 0. Why? Because 0 minus 0 is 0. The height factor of 78, okay, is not 0. The height of 50 is 2. The height of 88 is 1. So 2 minus 1 is 1. So the height factor of 78 is 1. What did I say? Well, I said that the height factor of any node can be either a -1, it can be a 0, or it can be a 1. Anything else, any other integer, is not allowed. We are not allowed to have a -2. We are not allowed to have a 2. We are not allowed to have a 3. The height factor must be in this range. So are the values here in this range? Yes, they are. We have 0 is in the range, 1 is in the range. Okay, this would be, the height factor here would be 0. The height factor here would be, okay, if the height is 1 and the height here is 0, 0 minus 1 is -1. So the height factor here is -1. The height factor here, let's see. All we do is we say, well, 2 minus 3 is -1. And so all of our height factors are in this range. So we now say the height is balanced. Okay, the AVL tree is balanced. This binary search tree is balanced. Okay, we can make that. This is an example. If we had any other value, any other integer with maybe 2 or a height factor, maybe you had a height factor for this particular subtree, maybe for the node 78, it was the height factor of 3 or the height factor of 2. Then you really can't say that this is height balanced. Okay, I hope that gets across. Right, so you can prove the height of an AVL tree storing n keys is O log n. Okay, and this just is an inductive proof saying that we'll always have a height factor, a recursive definition of the height factor going through between that range. Okay, this is not a very difficult proof, but even though I won't examine this proof in your assessments, it's still a good thing to learn. Just inductive proofs in general is a good thing to learn. This one is particularly easy, but I think as a mathematician, you should have a few mechanisms to prove things. The first is proof by contradiction. I think that's the simplest way of looking at things. That's assume the contrary and then try to find a paradox, try to find a ambiguity. That both scenarios can't be true, and then you assume that the one is true. Obviously, these must be tight scenarios. It's either one or the other. So that's proof by contradiction, and this is an example of proof by induction. And this is a very nice proof. You prove the base case first, and then you prove recursively. Right. So inserting into a binary search tree is particularly easy, and you've seen before. It's very simple. If I wanted to add the number, I don't know, 28 to this tree, all I would do is I would start here. I would compare 28 with 44. Okay, it goes to the left. I would compare 28 with 17. It goes to the right. I would compare 28 with 32, which means that 28 goes here. Okay, I hope this makes sense. I see it's starting to rain. I hope it doesn't affect the recording. Okay, I'm just going to continue. So 32 and 28 goes on the left hand side of 32. Okay, that's inserting into a binary search tree. And we always do this by expanding the external node. Okay, so what could happen in a binary search tree if it's an AVL tree? Okay, what could happen is an insertion could cause the tree to not be balanced. All right, so let's actually see if this tree is height balanced. So if we add this, we inserted a node 54. Okay, 54 trickled its way down the tree and ended up here. I'm just going to close my window so the rain doesn't affect the recording. Okay, so 54 will end up on this side of the tree. And what we will need to do now is check if the tree is height balanced. So let's do that. We start here. Well, first thing to do is to find the heights of every node. So let's do that. I just have a concern that I won't be able to switch colors. So if I write in blue, and then if I switch to green, you see the whole thing switches. Okay, maybe we'll have to do this differently. I will have to cut and paste this in Microsoft Paint. So print screen, paint, paste, and we can now write in different colors. Okay, so if we do this, we're gonna find that if the tree is balanced. Let's start off with black. All of these will be a 0. So this would be a 0. This would be a 0, 0, 0, 0, 0, 0. Okay. And here's a 0, here's a 0, here's a 0. Okay, great. So this will make this a 1. This will be a 1. This will be a 1. A 1. Sorry, this isn't a 1. This would be a 2. This would be a 2. This would be a 1. This would be a 1. This would be a 2. This would be a 1. This would be a 3. This would be a 4. Remember, we just take the highest and we add 1. This would be, this is a 4, this is a 2, this will be a 5. Okay, so let's now see what happens if I've inserted the 54 into a balanced tree. So let's just double check this. If I made a mistake, and it looks like I haven't made a mistake. This is 1, that's 4, 1, that's 2, that's 5. Okay, so in this case, let's take another color and put the height factors in. So I first put the heights in. Now I'm going to put the height factor in. Okay, so now it means we're subtracting the heights of the children. And we must get within the range of -1, 0, and 1. So 54, subtractor is going to give you a 0. This 1 minus 0 is going to be a 1. This will be a 0. Okay, 1 minus 2 is -1. It's fine. Okay, 0 minus 0. 0 minus 0 is 0. 3 minus 1 is 2. So we found the problem. All right. Okay, so I'm going to put a 2 here. Let's continue to search, right? So we're going to continue to write the height factors. So this would be a 0. This is going to be 0 minus 1, which is -1, which is acceptable. And then we see that 2 minus 4, okay, is -2. So we see there's a big problem here. When we were going up the tree, the first place where we got the error was here. Okay, this is the error because we're not allowed to have a height factor for any node greater than 1, strictly greater than 1, or strictly less than -1. Okay, in other words, The only height factors that are allowed, as I've said before, is going to either be -1, a 0, or 1. Okay, so this is not allowed because it's a 2. So we know that the height factors are violated at this point. And that means that we're going to have to do something because we want a balanced tree. But I'll just tell you what to mark, and then I'll show you how to handle this. But we need to recognize where the error is occurring. That's what we're doing here. So we need to mark the error. So I marked it here in red. This is where the error is occurring. Okay, I need to fix it. And fix in this case means I need to restore this tree to be balanced because it was balanced, and then I performed a insertion which made it not balanced, unbalanced, and now I need to fix it to make it balanced again. And we're going to do that by using a procedure, the housekeeping of the AVL tree. And I'll show you what that procedure is. But before we get there, we need to first mark where the error is occurring. So we see that the height factor is violated at 78. What we do then is we pick the largest height of the two children, which is here 50. So I'm going to make a circle around 50 to indicate that. Then I pick the largest height between 50's two children. And that, according to this, well, the height share is 1, the height share is 2. So I'm going to pick 62. So I found here a pattern. And now we've got to think about how do we handle this pattern? How do we deal with this pattern? So let's go back to the slides and we'll see how to do this. So the way we do this is that we recognize what pattern do we get. All right, so we start off there. So look at this. What pattern is this? Okay, you see that it goes from this node 78. It's moving to 50. Then it moves to 62. So the 50 is the left child of 78 and 62 is the right child of 50. Can you see there's a pattern that emerges here? I'd like to show you, if I could just cut something out here, what pattern we achieved. Okay, so we got this pattern. 78 was here. 78 was like this. Okay. I'm writing with my mouse, so I do apologize if it's illegible, but I'm saying it while I'm writing it. So you can write it on your piece of paper and you can try to like see if it's you can work with your own handwriting. So this is the 78. The left child of 78 is a 50, so I'm going to write it here. Okay, let's do that. And then the right child of 50 is 62. Oops. Right. And we notice that there may have been subtrees. Can you see this? These are subtrees. These are all subtrees. There may have been subtrees associated with these nodes. That means 50 could have had a subtree here. Okay. 62 may have had a subtree here. As the left child. As the right child of 62, there may have been another subtree. As the right child of 78, there may have been another subtree. And we see that there could have been 4. All right, there's a possibility. You may have had external nodes. Like here, for example, this subtree here was an external node. According to this, you can see it. Okay, you may have had external nodes, but it doesn't matter. Whether it's an external node or not, it's still a subtree. And I turn your attention to this pattern, which says it's a specific kind of pattern. It goes this way and then this way. It's a specific kind of pattern. And this specific kind of pattern has a way to handle. We have a way to restructure this pattern. So, okay, the most important thing here is that you recognize the pattern. Okay, that's important. If you don't recognize the pattern, you're going to have to spend some more time on this slide. There is a pattern here, and there is these subtrees associated with that pattern. Good. Let's go back to the trinode restructuring slide. So you see there can be different patterns. You could have a pattern like this, where you have a node, or a right child, another node, right child again, another node, and then the associated subtrees. Okay. If you have this pattern, you simply restructure to this pattern. You can think of the A falling down, and the B now is on top. Can you see? So A goes to the left subtree of B. B becomes the root, the hypothetical root. Remember, there could be another tree here, but I'm just saying it goes on top. And then C will be the right child. So that has its associated subtrees. Or right, this is one particular pattern. Okay, this side here. Here's another particular pattern. Okay, so A could be here. The right child of A could be C. The right child of C could be B. And you could have this right child, left child, okay, and the associated subtrees. If you have that, then you need to twirl around. So can you see these two here swap into, go into this A, B, C, okay? These two twirl around, okay, which gives us this. And then this is exactly like this. Oh, now it's doing it. Okay, anyways. This is exactly like this, which goes into this. Right? And that's how we get this. So you have A, C, B. A, right child is C, left child is B. B and C will twirl around to give us this structure. If you can't see, I'm writing it now again in red. Okay? B and C twirl around to give us A, B, C. A, B, C is exactly this ordering here, this structure here, which simply, as I said before, becomes this structure, which is the same as the structure. So you could go from here directly to this. Okay, hope that makes sense. Yeah. So we see that there's two scenarios here. This is the one particular ordering. This is another particular ordering, right? And you could have the case where you go directly from here to here, or if you have this case, you first go from here to here and then to here. Okay, or in other words, from here to here. Okay, I hope this makes sense. If it doesn't, I invite you to check out the textbook because it has a different explanation of this if you didn't understand mine. Great. So, so now we've got to actually, let's perform this insertion and see what happens, okay? But I want to show you, this is very difficult to write on this. Or maybe I can. Let me just zoom in then. I can zoom in and just try to write next to it. Okay. So, suppose you've got this tree. Okay, and this tree, as it says here, insertion example, continued. Okay, so remember before we had this 54, which was inserted into the tree, and it caused the tree to be unbalanced. Okay, so now, like I said, and we saw the example here on this paint example, where the unbalance occurred. So looking at this pattern that emerged, right, you got 78, the left child is 50, the right child is 62. Which one of you can tell me, oh well, if you can write it in the comments if you like, what the restructuring will be. So here your A is 78, your B is 50, and your C is 62. Okay, right? So we need to twirl around. Remember what this looked like before. All right, this is exactly this, but the reverse. So you need to twirl it around, twirl the bottom two around to get the straight line, and then from the straight line you get this. So even though it's mirrored, you can still do it. So we're going to twirl around 50 and 62 to get something like this. I'm just going to delete this. We're going to twirl around 50 and 62 to get something like this. So you're going to have 78. The left child is going to be 62. The left child of that is going to be 50. Okay, you get this, and then what do? And then you use this restructuring to get this, but it's mirrored. Okay, so we're going to then say, okay, from this, we simply have to bring up the 62. So all we do is we bring up the 62 by saying 62 is now here, 78 is now the right subtree, and 50 is the left subtree. I hope this makes sense. Okay, you can see it in your head, all right, how the restructuring occurred. And how did we find the pattern? We looked at where the height factor was violated. We then picked the largest height of the two children, which was 50 in this case because 3 is greater than 1, which gave us the second, gave us our B. And then we picked the largest height of the second of 50's two children, which in this case was 62. And that gave me the pattern. Okay. And from the pattern, I was able to use the restructuring methods of the AVL tree. Okay, these are the trinode restructuring. And from that, I now got I now managed to balance the subtree. Okay, so in this example, they found the height factor was violated here. The largest height was 50. The largest height was 62, which is the same thing that we did. And then they simply twirled around 62 and 50 and then brought 62 up, just as we did here. See, 62 is now on top. 62, 50, and 78 is now the same. 62, 50, and 78. Okay, take note of how the subtrees are organized. Okay, this was, and before I said you need to organize those 4 subtrees. T0, T1, T2, T3. Okay, T0, T1, so the left child of B, T2 and T3 would be on this side. Notice that the ordering of the subtrees will always remain, right? So from here to here, the ordering is the same. From here to here, the ordering is the same. From here to here, the ordering is the same. And from here to here, the ordering is the same. So all you got to do is, before you restructure, mark your subtrees. And after you restructure, connect your subtrees. So let's look at how it was done on the next slide. What they did was, this was your TO, this is your T1, this is your T2. Even though it's just one node, even though it's external, it's still your T2. It's a subtree. By definition, it's a subtree. No matter how you cut and dice this thing, as long as you're cutting and dicing consecutive elements, it will be a subtree. Right child of 78 is still a subtree. So you have your subtrees as they appear before you restructure. You will maintain that after you restructure. So your T0 will be the first, 50's left child. Then your T1 will be 50's right child. Your T2 will be 78's left child. And your T3 will be 88. It's not difficult. It looks difficult. If you're looking at this and trying to investigate how these subtrees were organized, you might confuse yourself. But if you just remember that the subtree sequence remains the same, then you will have no difficulty. Because all you got to do is disconnect the Lego blocks and reconnect them when you're done. And then you check again. Is this tree height balanced? And if it is, then you stop your restructuring. If it isn't, you then continue to restructure. But you only restructure going up. So you've now finished 62. You assume that this entire place is balanced. You now can move up and continue to find out if this tree is balanced. So, and if it isn't in a particular point, you find the pattern and you rebalance. As simple as that. What I would like to say, one more thing, is that the complexity here. So every time you check if something is high, every time you fix this restructuring or you restructure a particular subtree, you may be tempted to check the height factor of all the below ones, of all of the nodes in the subtree. Well, you don't, because it will be balanced, which means that you'll only perform if k is the amount of time it takes to restructure something. If k is the amount of time it takes to perform a trinode restructuring, then you'll only ever need k log base 2n, because you're only going to be restructuring with respect to the height of the tree. So this will be the cost of a complete restructuring. So it's k times log base 2n, where k is some small constant. K is just the number of restructurings you'll need to do, which is very small. So you can even say the complexity is O log base 2n. Because you're just restructuring with respect to the height of the tree. Remember, k is very small because all you're going to be doing here is just removing pointers around. Okay? If you look at this, k is just the amount of pointers you're going to move around. So in this particular case, you're moving a pointer here and there to get this. Here you're moving a pointer here and there to get this. Okay, but yeah, but you actually doing like, I mean, moving pointers around in memory is so cheap. It's not like swapping in arrays, right? It's just moving linkless pointers around, which is very which is constant. It's a small c, and so it falls away because constants fall away. For example, if this was a 2 log base 2n, you would just throw the 2 away. If it was a 10, you just throw the 10 away, and so on. I hope that makes sense, because that's what students find the most complicated in AVL trees. And it really isn't. I hope you agree with me that it really isn't complicated. So looking at restructuring in single rotations, you could have the situation where you got a line like this. Okay, we've seen that before. This was the one we saw in our example, but you've seen this before. You can also see this. If you have this, it's simple, like I said before. You're just going to be pulling B up. The subtrees will remain the same. Easy, single rotation. You're rotating this way. Here, a single rotation again. You're rotating this way. Your B is pulling up. A double rotation, and in this case, you could have this. Okay, this is the one we saw in the previous example, but you could have this as well. And if you have this, you simply twirl around B and C. Okay, and then you twirl around B and C, and then you come here. And that's easy. That's why they call it the double rotation, because you need 2 single rotations to get it right. Here you twirl around A and B again, and then just pull up A. Just pull up B, and here you go. So in other words, when you twirl around A and B, just moving it across, you end up here. And when you're here, it's very easy to get here. So that's why they call this a double rotation. Yeah. Okay, so then those are the only 4 rotations you need to worry about. As long as you can remember that, you'll be fine. So removing is very much the same. I won't say much about it because it's very much the same as a binary search tree. We spoke about that before. Remember, there were 3 situations in deleting nodes before in binary search trees. You remove the same way. Okay, you remove the same way. But once you remove the node, you then need to perform any amount of rotations to get the tree back into its balanced state. And so the removal operation is the same. You do it, and then you find the node that causes the imbalance, deduce the pattern, and then perform your restructuring. And you'll only need to perform k restructurings, where k is the you only need to ever perform, in the worst case, log n restructurings. K is a constant, which is just moving the arrows around for the restructuring, i.e. moving these arrows around. But you'll only ever need to perform log n of those, because log n would be you would assume that before you perform the removal, your AVL tree is balanced. Because remember, after addition, after adding things in, you're balancing. After removing things, you're balancing. So your AVL tree will always be balanced. Which means that when you are removing a new thing, you are working from a balanced tree. And because it's a balanced tree, it'll be log base 2n. Okay, so like I said before, this is the same story. Deduce the pattern and restructure. Okay, you can try some examples out. Great, so congratulations, you've learned about an advanced data structure. This data structure is extremely useful because from the other data structures that we've learned, the other tree-based ones, in the binary search tree, for example, we found significant computational difficulties. We could have worse cases. We could have the case where in a binary search tree, if you were given keys in increasing order, you would end up with a string. You would end up with a string of values, right childs. If you don't believe me, you can go to the previous video, but I'll just show you an example. In the old case, when you were inserting values in increasing order, you could have this case. Okay, you could have 1 and then 2 will come on the right subtree, then you insert a 3 which comes as the right subtree, then 4 will be the next right child, 5 will be the next. Look at this. This is computationally demanding. If you're searching for 6, it's the same thing like searching for 6 in a linked list. It's ON. But now, since we can keep our tree balanced, right? since we can keep our tree balanced by performing restructuring, okay, I'll show you an example. So here we are inserting into a binary search tree, right? 1, then 2, then 3, and 4, and 5, and 6. Now let's just insert the same things into an AVL tree. So 1, that's height balance, that's fine. Then we insert 2, oh, that's height balance 2, that's fine. Then we insert 3, oh, here's the pattern, I need to restructure. So I'm going to get 2, 1, 3. Now I'm inserting 4. Now I'm inserting 4. How do you move everything? Okay, now I'm inserting 4. 4 comes here. Do you see? It's always we're gonna always have a balanced tree. Then I'm inserting 5. 5 will be here. Then I need to restructure. So it's gonna be 2, 1, 4, 3, 5. And I'm height balanced again. Okay, I'd like you to continue. Add 6, add 7, add 8. But notice that here, compare the search time for this and this. Oh, I've deleted it. Okay, but compare the search time looking for 6, for example, or looking for 5 from this tree, this AVL tree, and compare it to this tree. Just looking for 5. Here we just need to go at most log n. Okay. Here we're gonna go on, which is terrible. So I hope you see the value of using AVL trees. Oh, sure, it might be more difficult to implement. Sure. Okay. The restructuring stuff will cost you maybe a page of coding, but look at the benefits in terms of computational complexity. So restructuring takes O1. I told you that before. It's just moving pointers around. It's constant time. Find takes O log n because it's a balanced tree. Putting items in it takes log n. Why? Because you're putting an item in, you first insert, which is log n, plus then you need to perform k restructurings, log n restructurings of constant time, which is log n plus c log n. And so that gives you 2 log n, and then the 2 falls away, so it's still log n. So that's put. Erase is the same story, all right? A computational the computational burden is log n. Yeah, so it's important to know that overall the computational complexity for AVL trees, whether it's find, put, erase, it's going to be log n. That's very important. All right. I hope you found this lecture useful. And I hope you now understand what AVL trees are. I would like to give you some homework. Can you please just take a piece of paper and ask, maybe you, I don't know if you have study groups, or if you don't have study groups, I recommend on what is this, Google Meet, or what is the other one, MS Teams. Maybe if you didn't, I mean, you guys are second years, right? So what you could do is, I'm guessing you might have made 1 or 2 friends before. Just 1 or 2 friends. If you're not me, you probably have friends, okay? So just pair up on MS Teams or whatever, and then work in groups and try to, even if it's a WhatsApp group, just give each other numbers and ask, build AVL trees yourself with a pen and page. Okay, or you can even program, if you understand it well enough, you can start programming it. But I want you to build AVL trees with integers and perform the restructurings. It's not obvious. These restructurings, you're going to need to practice them. They look very easy. I hope I explained it in a way that make them easy, but I do recommend inserting items yourself into an AVL tree and trying to learn the cases. There might be some tricky cases of restructuring, some things you can't pick up, but everything here is rule based, right? There's no heuristics. It's rule based. If you have this, then do this. If you have this, then do this. Okay, so that's important. There aren't any gray areas here. So yeah, I hope you found this lecture useful. All the best, and until the next one.